Welcome back to ChemCalcs, guys. This is Mr. J here. Today we're going to be talking about two additional gas laws, which combine some of the ones that we've already talked about and some of the variables. So the combined gas law is going to combine two of them, and then the ideal ends up combining most of the variables that we have talked about. So the combined gas law allows us to look at gases when we're changing two things. So far, all the laws we've talked about, we've only changed one variable. But the combined gas law allows us to change both temperature and pressure. And what we see is actually a combination of Charles and Boyle's law. If we look at the equation here, we can see the top part of this is Boyle's law, and then when we're looking up and down, we can see Charles' law in there. So we can easily combine them into one equation. Since we've worked these pretty good already, let's go ahead and jump into a quick example problem. So if we have a gas that occupies 15 liters at 800 torr and 96 degrees Celsius, what would be its volume at 706.8 torr and 68 degrees Celsius? A couple new factors in there. We talked about torr before. Remember, torr is basically the same as millimeters of mercury. It's a measure of pressure. And then we see our temperature is in Celsius, so we're going to have to convert that to Kelvin, right? All we have to do to convert it is to add 273 degrees. So let's go ahead and take the information we know and plug it into our equation. So what's our first pressure? Well, we have 800 torr, and our volume is 15 liters. Our temperature that we need is 96 degrees Celsius. It's in Celsius. We're going to add 273 to make that into Kelvin. And then on the other side, we're searching for volume. We have a P2 of 706.8, and then a temperature of 68 degrees Celsius, which will convert into Kelvin. So when we put this in our equation, it looks something like this. Okay, and so to solve for volume, once again, simple algebraic manipulation. We're going to multiply this side by 341, and then divide this side by the 706.8. When we do that, we find out that our volume will look something like that, and when we do the calculation, our volume comes up to 15.69 liters. Okay, so once again, it shouldn't be anything too difficult. If you're still struggling with those manipulating the variables, please come and see me. We'll do it together. Okay, let me have you try this one on your own. So a gas that occupies 42.3 milliliters at 24 degrees Celsius and 725 millimeters of mercury. What will be its volume of the gas at 12 degrees Celsius and 750 millimeters of mercury? So pause the video and go ahead and solve this. Remember, you're going to have to get that temperature up to Kelvin. Okay, and once you've solved it, hit play again and see if you did it correctly. Alright guys, let's take a look and see how you did. So we're using the combined gas law again. Alright, P1, V1, T1. If we look up here, we can see our variables. Here's our volume, here's our temperature, we got to convert to Kelvin, and then here's our final pressure, and then we want our V2 here, and then they give us temperature and pressure as well. So if we put it in plug and chug, we get something like this. Once again, we need to solve for V2. Okay, and when we do that, we're going to get 39.24. Hopefully you got the right answer. If you didn't, take a look at what we just went over, and if you can't figure it out, once again, please come see me and we'll get it figured out together. The second law we want to talk about today, and our final law, or at least for this section, is the ideal gas law. And the ideal gas law is going to bring together all these variables we're talking about. So it's going to relate pressure to volume, to temperature, and the number of moles of what we call an ideal gas. And what we mean by ideal gas is it's a gas that follows all the gas laws perfectly. It doesn't deviate from them. So things like we're going to have a collision between the atoms and molecules. They're going to be perfect elastic, meaning we're not losing energy. Okay, there's no intermolecular attractive forces between those molecules. Okay, so if a gas follows these, we can use the ideal gas law. And the equation for it is this: PV equals nRT. Okay, most of these variables we've already seen, right? P is pressure. In this case, it must be in atmosphere. It is important that it's in atmosphere, not in torr or millimeters of mercury or pascals. It's in atmosphere. Volume is going to be in liters, not milliliters. Okay, T is in temperature, as always in Kelvin. N is going to be the number of moles, And now R is a new variable. R is what we call the gas constant. Constant is a number that doesn't change. And so our gas constant for us is equal to 0.082 liters per atmosphere over moles per Kelvin. This is what we're going to use. Now, depending on what these units are here, we can get a different numerical value for those. And if we need one, I will give you those values as well. But generally, we're going to stick to this one here. So let's try a problem. So what is the volume occupied by 0.54 moles of N2 at 15 degrees Celsius and 0.97 atmospheres? So if we look at our equation there, we're solving for V. Okay, so if we plug everything in, pressure, what do we have here? We have 0.97 atmospheres in there, volume we're solving for, N is 0.54 moles, temperature is 15 degrees Celsius, which we will convert into Kelvin, and then R is our gas constant. Right. We arrange this for V, we get V is equal to nRT over P. When we solve it out, then it looks something like that. Now, notice with our gas constant here, I put the units kind of a different color so we can see how everything cancels. When we remember, the slash means that we put the moles in Kelvin on the bottom, so the moles are going to cancel there. We get our Kelvin temperature change, and then our atmosphere changes. So the only thing we're left with in this case is liters, which is what the problem is asking for. So it turns out it's going to be 13.19 liters. So pretty easy there. We just got to remember what our gas constant is. Let me have you try this one on your own real quick. Pause the video and then come back once you're done. No, really, pause it and do it. I'm talking to you. Please stop cheating. Okay, try this on your own. Alright, so let's see how you did. So PV equals nRT. We're trying to find for moles this time. So if we just write it straight out, we get this. Now we need to rearrange and solve for N. So we're going to take this side divided by those two. Alright, so N is equal to PV divided by RT. It looks something like this. And now, moles for Kelvin are on the bottom. Remember, when it's on the bottom, we can actually write the units on top as well, following your basic math laws. If you're not sure on that, come see me and we'll spend a little more time talking on this. So when we solve for N, we find that N is 27.04 moles of chlorine. Alright guys, so I went through this pretty quick, but we've spent a lot of time already talking on gas laws and how to manipulate them. So hopefully these were nothing new. The key to these is figuring out what information you have and which one of the gas laws, Charles, Boyle's, Lussac's, Avogadro's, now the combined gas laws or the ideal gas laws, figuring out which one is going to be the best one to use in a given situation. So we will spend some time in class working on that. As always guys, if you have questions, please come see me before class, or if you're thinking of any questions right now, write them down on your notes and we will address them as we go over this material in class. Until class guys, take care and we'll talk to you soon.